Alright, so in this lab we're going to look at Karnaugh Maps, and what they are tools that really make our lives simpler. Instead of using Boolean theorems to simplify complex problems, you can use this grid, this Karnaugh map, to find a simple algebraic expression from a truth table. And it consists of a grid with ones and zeros in it, each one of them corresponding to a min term in a function. The process of using the Karnaugh map is pretty simple. It's 4 steps. You sketch the grid, you fill in ones and zeros, you circle groups of ones with a couple of simple rules here, and then you write an equation from that. The best way to learn how to use Karnaugh maps is by example. So I have an example here where I have a truth table, and the inputs are A, B, C, and the output is F. And our goal is to figure out what equation goes right here that gives me a simple solution, and then therefore I can get a simple circuit sketch for that. The way you make a Karnaugh map is you need to have one square for every row of the truth table. So what we want to do here is make a grid, maybe neater than the one I have right here. And you have 2 axes here. So one axis can be corresponding to the value of C, and the other axis can correspond to A and B. So the values of A and B can have either a value of 0, 0, A is equal to 0, B is equal to 0, 0, 1, and then 1, 0, and then 1, 1. And you notice I went out to the right-hand side to essentially write the number 2 out there, and then 3 is over here. The Karnaugh maps will only work if you have this flip-flopping at the end of the order of these ones and zeros. We'll get into why that is a little bit later on, or it might become apparent as we work through this. And then for the C-axis, we have possible values of 0 and 1. So in this cell right here, this cell right here, it corresponds to A, B, and C being equal to 0. So we can see that that case right there is a 0. Then we have 0, 0, 1. So that cell, row right there, we put a 1 like this. And we continue going through the process, and we see that those 2 right there go right here. These 2 right here go over here. And lastly, we have those 2 right here. So let's see if I can get back to those rules, going back over to the PowerPoint where I was a moment ago. We want to circle groups of ones, and here's the rules that we want to look at here. We want to circle the largest groups possible, and we're only allowed to do groups of 1 by itself, or 2, 4, 8, 16. They can only be that size, and they can't be diagonal. So you can't circle groups of 3 or 5 or anything like that. It's got to be 2, 4, 8, 16, 32, etc. And you want to minimize the number of circles. You can do some overlapping, but every one must be circled. All right, that might sound kind of confusing, so let's just look at an example here. So one thing we can do is see that there's this group of 4 ones circled together like that. And that's the biggest circle of ones that we can make. Notice I'm not doing any diagonals. I just have basically a 2 by 2. So I followed my rules there. I have a group of 4. Here is a group of 2 right there. I'm going to get over talking about this last one here by itself in just a moment. But what we want to do is from that truth table, we're really down to step 4 now, writing an equation directly from the Karnaugh map. What you want to do is look at these 4 numbers that are in that group and look at whether these variables A, B, and C change. And if they do, you don't put them in. As I go through these 4 ones like that, notice that A stays 1 through all 4 of those. So then I just write A, and notice it's uncomplemented because A stayed 1 in all 4 of those cells. B changed, so I do not include it in my term down here. Also notice that C changed, so I don't include it as well. Alright, and then I can say or, go to my next term here. And you can already see that this is a simpler approach than using all the Boolean theorems to write out all the min terms for all of these terms and then try to simplify it using various theorems to get to the solution. We've already got to a fairly minimum solution. And there's 3 terms in here, but that's one of them right there. The bigger the circles you have, the smaller the term. This one right here, you see that we have 2 ones right there. And you can overlap them. You want to make biggest circle as possible. The best we can do here is do a group of 2. Notice that A changes, so we do not include it down here. B stays 1, so we include it as B. C say 0 going from there to there, so we put a C prime on that. And that's the second term. Now in this last one we could do a couple of things. One of them, we can just circle this 1 by itself, and you see that that means it's got to include every term in there. And that means it's going to be A prime because A stayed 0, B prime because B is equal to 0 there, and then we have C. And that's a pretty simple equation. You know, we could do a circuit sketch down here for that. It's pretty simple. But is it possible to get simpler? Well, the thing about the Karnaugh Maps is that you can actually do wraparounds. So you could wrap this group right here around over here. It's not really a group, I guess. We can just group this one right here with that one over there. So it's possible to do wraparounds to get groups of 2, 4, 8, 16, and 32, or you could just do 1 by itself. Now what we need to do is modify that one. Since we did a bigger group, let's see if this reduces this last one right here to fewer terms. See if I can get the eraser tool on that. Alright, so now what we do is we look at what changed. I'm going to see if I can mark this here. Notice that A went from being 0 here to 1 right there. That means we do not include it down here. B stayed 0 as we went from right there to right there. So it stayed 0, so we want to put a not B there. And C stayed 1 as we went in that wraparound. It stayed 1, so we get a not C like that. Alright, so that's pretty powerful. We got to a fairly simple solution. One of the things that I see right here, though, is that you can get one step simpler. Karnaugh Maps will always give you a sum of products, SOP, sum of products. So there's the sum, which we call ORs, and then the products, which are the ANDs there. This is a sum of products. It will only give you a sum of products. It will not identify cases where you could use an exclusive OR. But if you look at some of the theorems that we had inside the inside cover of our textbook, you'll notice that these last two right here will simplify it even further so that I get A OR, and this is B exclusive OR C. Now if I were to try to sketch this circuit right here, I would need a lot of gates. I would need 2 OR gates because of this OR right there and that OR right there. I'd also need 2 NOT gates because of that and that right there. I need 2 AND gates. I need a lot of gates here. But if you look at this simple solution right over here, I just need an OR gate for that, and I need an exclusive OR there. So I can really make my life easier if I use the Karnaugh map in combination with Boolean theorems such as those that allow us to express the exclusive OR. Alright, so let me continue on in the next video for more complicated Karnaugh maps.